Hey everyone, we are back and ready to do some more awesome pre-calculus. Yes. So here we are. We're going to do chapter 3.4, which is properties of logarithmic functions. You learned some of the properties about the secret Cheverton recipe, but now we're going to learn how to use different properties of logarithmic functions and how we can use those to solve problems. So let's get a new page. Goodbye, colorful page. Boop. There we go. Okay. So first of all, you need to remember if you have, oops, not that, x squared times x to the third power, what do you do with exponents? Oh yeah, we add them. That's right. So this would be x to the 2 plus 3 power, right? X to the fifth. So when we multiply functions together, then we add the exponents. And this is similar to logarithms in that if we have log base b of two numbers, r times s, that is not an s, then we can write this as log base b of r plus, I got to move my photo, log base b of s. Okay? Can I fit my up thing up there? There we go. So log base b of r, log base b of s, and I don't know if that shows or if the photo's in the way, so let me write it again. Log base b of r plus log base b of s. So when we're multiplying inside the logarithmic function, you can split them up into a sum, okay? That's a very useful thing. Let me get my lasso tool and get rid of these guys. Okay, so now, so this is referred to as the product rule. That is not a P. We have a quotient rule. And you recall x squared over x cubed. We would write this as x to minus 3. We would subtract the exponential. So incoming cat. Come on down here. There you go. So that would be x to the minus 1 in this case. So we have the similar kind of rule with logarithms, because logarithm multiplying is like dividing and dividing is like multiplying. If I have r over s, I can write this as log base b of r minus log base b of s. The denominator ends up being the negative term here, just like the denominator here ends up becoming the negative term there. So this is what we do when we're dividing inside a logarithmic function. We can split it up as a difference, as subtracting the two logarithmic functions. Okay, and lastly, we have the power rule. And that is x squared raised to the third power. When we raise an exponent to an exponent, we would write this as 2 times 3, or x to the sixth. And we have a similar rule with logarithmic functions. When we log base b of r to the c, when we raise this to an exponent inside the logarithm function, so this is inside the log function, this is not log base b of r raised to the c. Oops. This is totally different, okay? We're not talking about this. We're talking about when the exponent is inside the log function, okay? Let me write that a little neater so it's clear, because it's very important to differentiate between the two. So log base b of r to the c. Okay, so this is going to be, the c is going to come out front, log base b of r. Okay? So when you raise it to an exponent like we do here, we put it out front and it becomes multiplication. We multiply the c into whatever the log function was here. And remember, it is not this, because if you have log to the base b of r to the c power, let's say to the second power, all that means is log base b of r times log base b of r. Doesn't mean anything else. There's no tricks here. You just got to crunch these numbers or do something or I don't know what. But it's not this. It's not the exponent outside of the log function. This is inside the log function. Let me put my pretty parentheses. There we go. Inside the log function. Very, very important. Okay. Okay, so I think that's all the new knowledge you need. Let me get a new page. So here's an example problem. Log of 2x. Wait, what's the base here? There is no base. Is it base 0? No. This is common log. This is the same as log base 10 of 2x, right? When it's not written, it assumes that it's 10. And so if we have log base 10 to the x, how do we write that? Well, we could break that up to be log of 2 plus log of x. Okay? And so if we had a number out here, now we could solve, because we could convert this to a decimal by hitting 2 and then hit the log function. And we could get a number, and then we could solve for x. Okay? So let's do that. Let's say this is equal to 4. So log of 2, where's Mr. Calculator? There he is. So log of 2 is 0.301. Oops. Plus log x equals 4. So now I'm going to subtract 0.301. 4 minus 0.301 equals. Okay, so log x equals 3.699. Now what do? Let's put a 10 there. What do we do? What do we do? Do the inverse log? Well, there is no inverse log function. You don't do inverse log. So when you're stuck, you use the secret Cheverton recipe for logarithmic jambalaya, and I write this in exponential form. So the base is 10, the exponent is 3.699, and the answer is x. So now I got to do 10 to the 3.699, and we'll see what we get. It's going to be a big number. Exponent 3.699, and we get, oh, look at that, 5,000. Well, 5,000.35. So that's what x is. Okay, so if we started out with 4 equals log of 2x, then we would break this up into 2 pieces. We'd calculate this one. We'd move it to the other side. We'd have log x equals 4. We'd use the secret formula, and then we would get the answer. Okay? Okay, let's look at another. Here is a simplification. Simplify so that there's no exponents. Okay, so log of 8xy to the 4th. So we want to spread it out in a bunch of individual log functions. Well, what's the product rule? It says when I'm multiplying inside here, I can change it to addition. Log 8 plus log x plus log y to the 4th. Oh, and then I got to do the exponent rule here. log 8 plus log x plus 4 log y. And this is this thing expanded and in its simplest form. Okay? Okay, let's try another. Because, man, these are fun. Holy mackerel. Okay. Natural log of square root of x plus 4 over x. What do you think of that? Now, that's fun. Okay, so we want to simplify this. Well, first of all, I see the quotient rule, so I can write this as ln of square root of x squared plus 4 minus ln of x. And then I see a square root that I could write square root of x squared plus 4, I could write as x squared plus 4 to the 1/2. So I can use the little exponent rule and bring that 1/2 out front. So this is x squared plus 4 to the 1/2 all inside there. So I'm going to bring that 1/2 out front. Now, is there a rule for when you're adding inside a log function? This is a spot where people get confused. Don't get confused. There's a rule if we had ln of x squared times 4, we could break that up into ln of x squared plus ln of 4, right? We could do that. But ln of x squared plus 4, you know what that's equal to? That's equal to ln of x squared plus 4. We can't really change that. That can't be simplified. So here's our most simple thing. Now, half of you are going to make this mistake right here, and you're going to say this is equal to 1/2 of ln x squared plus ln 4 minus ln x, because you're not going to do all the homework problems, and you're probably not going to watch this video, and so you're going to go to do this, and you're going to make that mistake, and we're going to be sad together. But don't make this mistake. Do the homework. Take notes. If you're watching the videos and you're not taking notes, you're not going to remember. Take notes. You always should take notes. Okay, here we want to combine. We want to get it into one log function. So we're doing the opposite of expanding. So this is 5 ln x minus 2 ln x plus 2 ln y. Okay, so how are we going to do that? Oh, wait, I wanted to do this. There we go. Plus 2 minus all that stuff. Okay, so first I'm going to deal with these coefficients out front. I'm going to move those into the logarithm function as exponents. Right? And what's the rule when we're adding exponents like this? What was the product rule? It said that if you had ln of a times b, you could write it as ln a times, that's ugly, times ln of b, right? And the same thing, log of a times b, you could write as log a. Oh, I did that wrong. You guys didn't stop me. What is wrong with you? I went too fast. So if we had ln of a times b, we'd write it as ln a plus ln b, right? The product becomes a sum outside. And likewise, log of a times b would become log a plus log b. And if it was division a over b, then it would be log a minus log b, right? So over here, we have in here, well, those are plus, so I'm going to write this as ln of x squared times y squared, right? And then I have subtraction. What does it mean when we're subtracting logarithm? Oh, yeah, this is the quotient rule. So this would be ln of x to the fifth over x squared y squared. This is condensed to its single form. So this and this are equivalent. And we're going to practice the rules of logarithms to go back and forth from we're going this way, we're condensing. And when we're going this way, we're expanding. Okay? Okay. Quiz time. Is it true? Ready? ln of x plus 2 equals ln x plus ln 2. What do you think? Yes or no? True? False? True? False. You cannot do anything to ln of x plus 2. It's stuck there. Okay. ln, oops, we're going to make this a log. Not that it matters. Log base 2 of 5x equals log base 2 of 5 plus log base 2 of x. True or false? Yes? No? Yes? No? Yes? Ding, 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 ding. True. We're using the quotient rule to take the product and split it up into a sum. Next one. Oops. Nah, that one's too easy. Oh, here we go. We'll do this one. Wow, this one's kind of obvious. Log base 5 of x squared is equal to log base 5 of x. This one's kind of easy. Oh, well. Log base 5 of x. There we go. True or false? True, false, true, false, 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 true, 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 false. What do you think? This is false because the exponent acts directly on the thing next to it. So this is saying x squared inside the logarithm. It is not saying log base 5 of x squared. That's what this is equal to. Okay, but when we look at this, what will we simplify this to? This would be 2 times log base 5 of x, right? The coefficient comes out front. Does not equal this. No, just like this one. No. Okay, last one. This is the last true false. This is exciting. We're going for the record. Log base 3 of 7x equals 7. Well, again, this is easy too. You'll all get this. True or false? True, false. True, 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 false, 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 true. This is false. This thing would be equal to log base 3 of 7 plus log base 3 of x. If we wanted it to be like this, then we would have to write it as log base 3 of x to the 7th, right? Like I said out here, the exponent comes out and becomes a coefficient. So this is equal to that, not that. Okay? Okay, that was fun. It was a fun little game. Hope you all enjoyed it. Feel free to rewind it and watch it again. Okay. Now, changing bases. 4 to the x equals 7. Let me write that a little neater. 4 to the x equals 7. Okay. So if we wanted to solve for x here, I could take, how do we do this? Well, I could write it in log form. So using the secret Cheverton formula, log base 4 answer exponent. So how would we do this? I don't know. What if I, just for fun, took the natural log of both sides? So I did the natural log of 4 to the x equals natural log of 7. Is that legal? Can I take the natural log of both sides? Of course you can. And what do I do here? An exponent inside the log function, this comes out front. X times ln 4 equals ln 7. And remember, ln 4 is just a number, just like ln 7 is. So I can solve for x by dividing by ln 4. So I get x equals ln 7 over ln 4. That's kind of interesting. And over here, so this doesn't help us terribly, but we're going to keep this in mind. But let's say instead of taking the natural log of both sides, I wanted to take the common log. So I wanted to do the log of 4 to the x equals log of 7. And again, the exponent rule, x comes out front, and we would get, oops, x times log 4 equals log 7. And again, I'll divide by log 4 to solve for x. So I get x equals log of 7 over log of 4. Well, now that's fun. Wait a minute. I got x equals log of 7, log of 4, and x equals log of 7 or log of 4. And I got this thing up here. X equals log to the base 4 of 7. Oh, so this is a way we can change bases. If I get something ugly like this, and I have to evaluate it, and I don't have a log to the base b of a, or I'm guessing it's probably x, y, like that. If you don't have this button on your calculator, then you are out of luck for evaluating this. But you can change this to be like that, or you could change it to be like this. So anytime you see a log function that has a goofy base that's not log base 10 like common log or natural log, if I have log of base b of a, I can write that as log a over log b, or I could write it as natural log a over natural log b. And this is referred to as the change of base formula. Okay? Where you can put log of a on the top, log of b on the bottom, or natural log of a on the top and natural log of b on the bottom. And this is kind of how we prove that that's legal. Okay? So you absolutely want to write this down, because you're going to use it and people are going to come to a test and they're going to get log base 3 of 7. How do you do this? And they're going to write it in exponential form. 3 to the x equals 7. And they're going to say, holy crap, I can't write this as a base 3. How do I do this? And well, you use the change of base formula to do it. And because you didn't do the homework and you didn't come in and ask for help and you have trouble with it, I'm going to say boo-hoo. Sorry. So log base 3 to the 7. This would be log of 7, which is a single button I can press on my calculator, over log of 3. So let's see what that is. Log of 7. I got to turn it on. Log 7 equals, boop, 0.845 over log of 3. Log 3 equals 0.477. Now I just got to divide. And I get 1.77 something. And by the way, don't write out 12 decimal places because it's not important, right? 2 decimals, 3 decimals, you know, if you end up with a really small number, 0.000163, you don't want to say it's 0. That's a huge mistake. But don't write out a million decimals because it's dumb. It doesn't serve any purpose. It doesn't say you're smart because those last decimals, whoops, the last decimals way out here, you know, these are totally random things because we rounded when I did this on my calculator. So the idea that these last decimals out here are actually true is a fantasy, okay? Give 2 or 3 decimals. We're not doing significant figures like you would in chemistry. We don't care. I'm looking to see when it looks for a test, we're gonna look to see how close these are, you know, that's all. Okay. Change of base. Okay, let's say you got to do one. Of course, if I say do this problem without using a calculator and you're doing it at home online, come on, you're using a calculator, right? Of course you are. But log base 4 of 16. Let's say we wanted to do this without a calculator. I come to your house, I take your calculator from you, and I hide it. So this is a change of base problem. Log of 16 over log of 4. And I see 16 and 4, and I'm thinking, I could do something to 16. I could write it as log of 4 squared over log of 4. And what do you do to the 2? The 2 comes out front as a coefficient. And log 4 is a number, and log 4 is a number, and they're the same number, and they cancel. Okay, so we get 2. By the way, let's say something. Log of x plus 2 over log of x. Okay, do the x's cancel here? Absolutely not. Do the log functions cancel? No, those are an operator. They cannot cancel. Does anything cancel here? No, nothing cancels at all. Can I break this up to log of x plus 2 minus log of x? Is that what the quotient rule says? No, it does not. You cannot do this. If you wanted to do this, it would have to be written log of x plus 2 over x. And then the quotient rule would let you write it like that. This thing here, you can't simplify anything. You can't do anything. That's just is what it is. And you can't change it. Okay, you cannot cancel log functions. You cannot cancel things from inside the log function unless you have pen. I mean, if they're the same thing, now you can cancel this whole thing and that whole thing because they're identical. But if they're not identical, if they're like that, you can't do anything to this. You can't cancel anything. So don't cancel from inside the log functions. If you have log of 2 times 1/2 x plus 4. Can you distribute the 2 into here and say this turns this into a 1 and that turns that into an 8? Do you distribute like that? No, you don't. The coefficient out here is the same as an exponent inside the log function, right? Exponents inside come out as coefficients. So there's a lot of very specific rules of logarithms you have to keep track of, and remember that you can't really distribute across a log functions. You can't cancel log functions. You got to be careful with these, okay? So there we go, property of log functions. We'll go through more of this during office hours and homework sessions, and if you need help, you need to come and get it. When you get to the test, if you haven't really worked on this stuff, you will get an ugly, ugly surprise when it's time to take the test, and you will be sad because logarithms, when you haven't practiced them, are hard. When you have practiced them, you find that they're pretty easy, and the more problems you do, the better. And all the odd numbered problems have answers in the book. and all the problems in the chapter review have answers in them. And so you can go and look at those. Lots of opportunities for problems, or you can come to homework sessions and you say, hey, can you give me some practice problems? And I'll say, sure. And I'll write some on the screen. Okay. Any questions? Come on, now's your chance to ask. Oh, nobody asked? Okay. We'll see you next time. Bye.